Good Wednesday evening, everyone. Welcome to the Chem Help ASAP live stream. So, as you can tell from the title, tonight we are going to be working titration problems. So we're going to start with the simpler one. We're going to start with a strong acid and a strong base, and we're going to work through several of those problems. And then we will work on a weak acid with a strong base. Once you get the hang of these calculations, you'll see how they start to repeat. And when you feel like you're starting to repeat yourself, that's actually a really good sign because it means that you are used to the calculations, you're comfortable with the calculations, and hopefully you can start predicting what happens next before I actually do the calculation. Okay, so thank you to my moderator for helping me tonight. And let's go ahead and jump on in. All right, so our first problem is asking what is the pH if we have a 15 milliliter aliquot. Now, an aliquot is just a sample of 0.2 molar nitric acid. Nitric acid, if you don't know, is one of the more common strong acids. So we've got a strong acid. So it's asking first, what is the pH of just this sample of nitric acid? Then we want to know the pH after we've added 5 milliliters of a 0.3 molar potassium hydroxide solution. Potassium hydroxide is a strong base. And then what we're going to do is we're going to add 5 more milliliters. Again, calculate the pH. So that would be at 10 milliliters of potassium hydroxide added. Then we're going to add 5 more milliliters. That will be at 15 milliliters of potassium hydroxide added. So what we're going to do is we're going to take this stepwise, and we're going to have 4 different calculations. So we're going to calculate the pH at different points in this titration. Okay, any questions before we start? I guess we haven't had too much time for questions. So let's go ahead and jump in. So the first thing that I want to do is I want to get the chemical equation for the reaction that's happening here. So let's get our pen up. So what we've got is we have a strong acid plus a strong base. And when you have neutralization reactions of especially the Bronsted-Lowry acids and bases, you are going to have an acid reacting with a base, and you're going to form a salt and water. So our salt here is potassium nitrate, and of course water is just H2O. Another way you can think of these reactions is they are double replacement reactions. Now, in that case, if you're thinking purely of double replacement, you might initially write your water as HOH, but of course we just combine that into H2O. Now, the nice thing about this reaction is we have a 1-to-1 ratio. So for every 1 mole of nitric acid is going to react with 1 mole of potassium hydroxide, and that is going to really simplify our calculations. And many of these titration reactions, at least initially, you're going to be working in 1-to-1 ratios. That way you can focus on everything else that's happening. So this problem is first asking us to just calculate the pH of our sample of nitric acid. So we have added no base to this reaction, and we just want to know the pH. Now remember that pH, I'm going to write the equation up here. pH is simply the negative log of our hydronium ion concentration. Let's call this step 1, and we'll say no potassium hydroxide added. So this is only our nitric acid for this calculation. Okay, so again, we need the concentration of our hydronium ion. Now the great thing about a strong acid is when we have nitric acid in water, it is a right-hand arrow only. This is not an equilibrium. It's going to completely ionize. So we are forming the hydronium ion and the nitrate anion. This means that our concentration of nitric acid will equal our concentration of hydronium ion. So this is a shortcut you may always know, but sometimes instead of putting your concentration of hydronium ion, you might see people writing in the concentration of, say, nitric acid. And this is why you can do that. It is a 1-to-1 ratio. Again, this is because it is a strong acid, only a right-hand arrow, only the forward reaction happens. This is really easy because we have been given our concentration of nitric acid. And so our concentration of nitric acid is equal 0.20 molar, which also equals our hydronium ion concentration. So our pH is simply going to be the negative log of our hydronium. These decimals are not showing up. And I have done that calculation. Our pH is 0.70. Now, this makes sense. We have a strong acid in solution, so our pH should not only be below 7, but it should also be very low because we've got a strong acid. So I always, at the end of these calculations, like to do just a little bit of a check to say, does this make sense? And yes, this does make sense. Okay, so our first part of this problem was fairly easy. Let's make sure we don't have any questions. Okay, so what we want to do next is we want to calculate the pH after we've added 5 milliliters of our potassium hydroxide. Now, our potassium hydroxide is a 0.3 molar solution. So our step 2 here, we'll say we have added 5 milliliters of potassium hydroxide. Okay, so let's go ahead and calculate our moles of our potassium hydroxide and our moles of nitric acid, because we're going to need to do some stoichiometry. And of course, when we do stoichiometry, we need moles. So let's see, we have added 5 milliliters of potassium hydroxide. So if we take our concentration and multiply it by our volume. Now, I have converted my 5 milliliters into liters, hence the 0.005 liters. And that gives me 0.0015 moles of potassium hydroxide. All right, so that's our moles of potassium hydroxide. Let's calculate how many moles of nitric acid we have in the sample, and that goes back to the aliquot, again, the sample. So we started with 15 milliliters, and the concentration is 0.2. So we just do the same kind of calculation. We take our concentration times our volume, again, converting our volume into liters. And we have 0.003 moles of nitric acid. Okay, so remember our reaction, we already have our reaction. This is what is going on right here. So we need to know, this is your basic stoichiometry question. This is actually a limiting reagent stoichiometry question. Now, the thing that's going to make this easy is we're in a 1-to-1 ratio. So I know that I am going to have excess nitric acid. So my potassium hydroxide is going to limit me. I'm going to use up all of my potassium hydroxide, and I'm going to have some nitric acid left over. The question is, how much nitric acid do I have left over? And I'll show you how I like to set these problems up. You can set it up as a traditional stoichiometry problem where you start with your limiting reactant, then you predict how much is used. But I use something very similar to the ICE table for equilibrium problems. So I'm going to rewrite my equation here. All right, so this makes potassium nitrate and water. And my initial number of moles is for nitric acid, I have 0.003, and for potassium hydroxide, I have 0.0015. Of course, I have no potassium nitrate initially, and water, again, just like with equilibrium, we don't really care about. Now, when you set this up for equilibrium, I know you're very used to writing minus x's and plus x's, but again, this is not an equilibrium. This is right-hand arrow only. This is going forward, and I know how much is going to be used. I'm going to use the amount of my limiting reactant, and in that case, that's the potassium hydroxide. So I know I'm going to use all of my potassium hydroxide. So that means I'm going to use 0.0015 moles of my nitric acid. And of course, I will form 0.0015 moles of potassium nitrate. Again, these numbers come from the 1-to-1 mole ratio. That's why I'm writing the same number in. If you had a 1-to-2 ratio, and you would have to take that mole ratio into account. But again, I have chosen this specifically because it is a 1-to-1 ratio. Now, what this means is when this reaction is complete, I don't have any potassium hydroxide left, and I will have 0.0015 moles of nitric acid. Again, I just subtracted these, and I do have a little bit of potassium nitrate in solution. Now, because we have a strong acid and a strong base, the amount of potassium nitrate formed is not of a concern for us because that is a salt that does not have acid-base properties. So we're really just focused on the nitric acid solution at this point. Now we go back to a similar problem like we did for our first step here. We just have nitric acid in solution, but we have a little bit less. So to calculate the pH, we need to know the concentration of nitric acid, which will be the concentration of hydronium ion, which we will use in our calculation for pH. Okay, so let's get our concentration for nitric acid. Well, we know from our quasi-ice table, again, remember, this is not an equilibrium, that we have 0.0015 moles. That is what is remaining. And now we just need the volume of our solution. So this is where we need to go back to the problem. We started with a 15 milliliter sample of nitric acid, and we have added 5 milliliters. So you can even write this in as 5 milliliters plus 15 milliliters plus our 5 milliliters of potassium hydroxide. Of course, that's going to be 20 milliliters. Now, the key thing here is, of course, you need to convert that into liters. But that will give you your concentration, and I have done that calculation, and we get 0.075 molar for our nitric acid. That is our concentration of hydronium ion. Again, we've got a strong acid. It's a 1-to-1 ratio, so it is the same concentration, which means when we calculate our pH, we're going to take the negative log of that 0.075 molar. Okay, and that will give us a pH of 1.12. So at this point, I like to do a double check. Does this make sense? And yes, it does. Again, we have a very acidic pH. We do have a strong acid in solution, so our pH should be very low. But I'm also looking at the fact that we started at 0.7 and now we're at 1.12, which again makes sense to me because we don't have quite as much nitric acid because some has been neutralized by the potassium hydroxide. Okay, that was a lot. Let's make sure we don't have any questions. All right, so that was our step 2. We added 5 milliliters of our potassium hydroxide. Now we're going to go on to step 3. So we're going to add 5 milliliters more. So that is going to be a total of 10 milliliters. So in this case, we've added a total of 10 milliliters of potassium hydroxide. Now, when you do this next step, there are actually 2 different ways that you can think about this. You can either take your situation that you have calculated in step 2 and add 5 more milliliters, Or you can consider if you kind of redid step 2, but instead of just having 5 milliliters, you would have 10 milliliters of potassium hydroxide. Now, the second way is the way that I am going to show you how to do these problems. I find that it makes a little more sense to students. But again, you do them how it makes the most sense to you. All right, so we're going to have to go to our next page. And, I realized I wish I had put the problem up on this page. I knew I'd have extra pages, but here we are. We can always go back and reference the previous page. So this is our step 3. We have added 10 milliliters of potassium hydroxide. And I'm going to go ahead and write in the concentration of potassium hydroxide as well, just so that we have that right there. So just like in step 2, I want to calculate how many moles of each I have. Well, the great thing is that the nitric acid is the same because it always was. You had the 15 milliliters of the 0.2 molar aliquot. So for my nitric acid, I still have my 0.003 moles. So I don't have to redo that calculation. This is one of the reasons why I like to approach it this way instead of taking step 2 and adding 5 more milliliters. I just find it's a little bit easier. Okay, so for our potassium hydroxide, though, that has changed because we now have 10 milliliters instead of the 5. So for our potassium hydroxide, again, we have the 0.3 molar, and this time we have 10 milliliters that we've added, so our volume changes, and that gives us 0.003 moles. All right, this is actually done on purpose because when our moles of acid equal our moles of base in a 1-to-1 ratio, which we do have, then we are at the equivalence point. So remember when doing titrations, your equivalence point is a stoichiometric point where your moles of acid equal your moles of base, assuming you've got a 1-to-1 ratio like we have. What we'll discuss a little bit more later is what's called an endpoint, and that is when you're doing a titration and you're using an indicator. But for this right here, because we're talking just stoichiometry, this is the equivalence point. Now, at the equivalence point, let's run through kind of our quasi ice table again. I'll just pop back here so you can see it. So what I'm going to do is I'm going to recreate this table down here, but with our new numbers. All right, so let's write our reaction. We have our nitric acid reacting with our potassium hydroxide to give us potassium nitrate and water. Okay, so I started with 0.03 moles of nitric acid. I have added 0.003 moles of potassium hydroxide. Again, I assume I have 0 here, and I'm just not even going to mess with water. Okay, so then the question is, which one of these is limiting? And it's a little bit of a trick question because you could think of it as both are limiting or neither are limiting. I like to think of it as both are limiting. So I am going to use up all of these moles. Oh, sorry, that should be a negative. And of course, I am going to form 0.003 moles of my potassium nitrate. So I have no nitric acid, I have no potassium hydroxide, and I have some potassium nitrate. Now again, potassium nitrate is a salt that does not have acidic or basic properties. So then what is my acid or base in solution at this point? Well, your most dominant acid or base is water at this point. So if water is your acid in solution, what is the concentration of your hydronium ion? Well, that is 1 times 10 to the negative 7th. Again, if you remember, maybe I'll put this over here. Remember that you've got several equations that you use when you're dealing with acids and bases in aqueous solution. So you might remember this equation right here. So again, if you have pure water, both your hydronium and your hydroxide concentration are equal, and they both equal 1 times 10 to the negative 7th. So to calculate our pH is simply the negative log of our concentration, and that equals 7, which you probably could have said from the get-go because we have a neutral solution. We've just got pure water, and of course the pH is 7. But this is why the pH is 7, is because you have a solution of water. Again, you do have a little bit of potassium nitrate, but it doesn't have any acid-base properties. So then your acid in the solution is water. So that's where this comes from and where a pH of 7 comes from. So that is what's going on at the equivalence point for a strong acid and a strong base. So that took a really easy point and maybe made it a little bit more difficult, but I want you to understand where that pH of 7 comes from. Okay, we have one more part, and I'm going to try and squeeze it in here. So our last part of this problem, let me just pop back here. So we're going to add another 5 milliliter, which brings our total up to 15 milliliters of potassium hydroxide. Again, I'm going to approach this in the same way. I'm going to say I have 15 milliliters of potassium hydroxide that has been added, and it is still the 0.3 molar solution. My number of moles of nitric acid is still the same. And now my potassium hydroxide is going to change. Again, my concentration doesn't change. Whoops. Sorry, I got a little happy with the zeros there. There is my concentration. But this time I have added 15 milliliters. So again, my volume changes. And now I have more moles of potassium hydroxide. Oops, this is also moles. I need to make sure I label everything. Okay, so I'm going to do the same thing again. I'm just going to do a stoichiometry problem. I think I'll move up here. So again, my reaction here is my quasi-ice table. Same as it's been, plus water. And I always started with my 0.003, and now I have added 0.0045 moles. So my limiting reactant has changed. Now, when I did step 2, my limiting reactant was my potassium hydroxide, but now you can see my limiting reactant is going to be my nitric acid. So I am going to use up 0.003 moles. That is a negative there. And of course, I will form this many moles of potassium nitrate. So now I have no more nitric acid left in solution. I have an excess of potassium hydroxide, and specifically I have 0.0015 moles of potassium hydroxide, and of course I do have some potassium nitrate, which I don't worry about it because it doesn't have any acid-base properties. So now I just need to find my concentration. Now here is where, again, it gets a little bit tricky. Because I'm dealing with a strong base here, again, potassium hydroxide is a strong base, similar to the nitric acid, I know my concentration of potassium hydroxide will equal my concentration of hydroxide. And once I have my concentration of hydroxide, I like to go ahead and calculate pOH and then calculate pH. But again, you can do this a multitude of ways, so just do it however it makes the most sense to you. So let's calculate this concentration of hydroxide. I know my number of moles. So my concentration of hydroxide is 0.0015 moles, and I just need my volume at this point. So this is another place where you can get a little bit tripped up because you want to make sure you get these volumes correct. So I had 15 milliliters of my nitric acid. That was my sample when I started with. And at this point in step 4, I have added another 15 milliliters of potassium hydroxide. So my total volume is now 30 milliliters. So that concentration is, I did this calculation, is 0.05 molar. Now again, when you do this, make sure you convert these milliliters into liters for your concentration. Sorry, that is the concentration of my hydroxide. So I am going to calculate pOH from this. That is simply a negative log of 0.05. And that equals 1.3. And from pOH, if you remember, maybe I'll write this up here, 14 equals pH plus pOH. So this is a very easy calculation. I'm just going to take 14 minus, I'll write it down, 14 minus 1.3. And that gives me a final pH of 12.70. This is equal to pH. And maybe I'll just box this here. Again, I like to do my does it make sense check. And yes, it makes sense because we have a base in solution. We have neutralized all of our acid. We have excess base, so we should have a pH that is above 7. It is a strong base, so it should be well above 7. So having a pH of 12.7 makes sense. This is where doing this check can help you if at this step, instead of realizing that you were calculating pOH, you thought you were calculating pH. It should raise some red flags if you thought your pH was 1.3, because of course that would be an acidic solution and you have no more acid in the solution, you just have base. So again, that's why I like to do that logic check. Does this make sense? Okay, so this is our titration problem for a strong acid and a strong base. Let's make sure that there are no questions. Let's see. It looks like Aaron had a question. Okay, great. Good. Aaron, I am so glad that you're finding these streams helpful. Okay, let's take a look at a titration curve. Now, this is a titration curve that I used from the OpenStax Atoms First Chemistry textbook. So if you're using that textbook, you might actually recognize this, this titration curve. This is a strong acid and a strong base. Actually, this is specifically sodium hydroxide, and you can see we've got a different concentration. So this titration curve is not actually the one that we just calculated. It's simply one that is very similar to it. Now you can see this also has an equivalence point of 7. So when you have a strong acid and a strong base, and they are at the equivalence point, you will have a pH of 7 because the salt that you form will not have any acidic or basic properties. And you can see you start down here at a low pH, it goes up just a little bit, and then you shoot up right here. Again, if you've taken calculus, this isn't a point of inflection. And then you end up very, very quickly with a strongly basic solution. So if you are actually in the lab and you are titrating this, what you'll end up with is you'll have lots of points along here. And then you can't add volumes that are small enough to get many points up here along this, the equivalence point. If you're very good, you might get 3, but if you see, like, so here we've got volume on the x-axis, you can see at this point, again, because it's a point of inflection, your changes in volume are minuscule at this point. So if you're very good at your titrations and you're very good at your splitting your drops, then you might get a couple of points along the titration curve in this area, but usually you don't because the pH just changes too fast. Okay, so that is the titration curve for a strong acid and a strong base. And now, let's see, yes, we've got time, good. I want to do a titration problem where we have a weak acid and a strong base, because you see it's similar, but it's not quite the same. Okay, so here is our problem. And you can see it looks almost exactly the same, and I did that on purpose. So instead of nitric acid, which is a strong acid, I changed this up to nitrous acid, which is a weak acid, and I have given the Ka in this problem for nitrous acid. So it's kind of amazing what the loss of an oxygen will do, right? So now when we have this weak acid in solution, it's not just a forward reaction, it's not just a right-hand reaction, it is in equilibrium. So we're going to have to take that equilibrium into account. Okay, but we're going to do the same thing. So we're still starting with a 15 milliliter aliquot. We want to know the pH initially. We want to know the pH after we've added 5 milliliters, after we've added 10 milliliters, and after we've added 15 milliliters. And I kept the base the same. It's still potassium hydroxide. It's still a strong base. So let's go ahead and jump into calculating the pH before any base is added. So this would be step 1, and we'll say, again, no potassium hydroxide added. So this is just pure nitrous acid. This is our weak acid in solution. Okay, so I kept these numbers the same so that we could do a little less calculation. So we have no potassium hydroxide, but for our nitrous acid, we have our 0.003 moles. And again, that's just like before. Actually, I can pop back to that page here where this calculation right here. Again, it's the same concentration, it's the same volume, so it's the same number of moles. So that is where the 0.003 moles comes from. All right, so now we have to do our equilibrium problem. And that is, we have our nitrous acid. It is in aqueous solution. So it is going to form some hydronium and some nitrite. All right, now I'm going to do a proper ice table. So I have 0.003 moles. Of course, I have none of this initially, and just like before, I'm just going to ignore water. I don't need to mess with it. I don't know how much of my acid is going to dissociate, so now I'm starting to use my x's. So again, for my my reactant side, that's minus x, and my product side is plus x. And for my equilibrium concentrations, I'm just adding this column up, and we've got this, and now we're going to use our Ka. So again, our Ka is our hydronium ion times our nitrite over our nitrous acid, and that is simply going to be x squared over 0.003 minus x. Again, this x squared comes from both of these concentrations are x, so I just went ahead and wrote x squared. Now, I really don't want to have to solve this using the quadratic formula, so I'm going to test and see if I can drop this minus x here, and very often in your weak acids you can, but let's test and see. So if I take my initial concentration of nitrous acid over my Ka, that is 0.2 divided by, here's my Ka, 4.0 times 10 to the negative fourth, and I get 2,000 for that. Now what I want to check is I want to see if that is greater than 500, and yes, that's definitely greater than 500, so I'm going to give this a check. That means that I can drop this minus x, so I'm actually just going to write through it, so I don't have to mess with that anymore. That makes this equation much, much easier to solve. So of course my Ka, I actually have a value for it. You know what? I changed my mind. Instead of writing it here, I'm going to go down to the next line. I think that'll make this a little more clear. So this is my value for Ka. That equals x squared over 0.003. So my value for x is 0.0011. All right, so here's where you have to remember what X is. And so X is right here. This is my moles of hydronium ion. All right, and I'm trying to get to pH. So if I'm going to do pH, I'm going to take the negative log of my concentration of hydronium ion, which I'm close to but not quite because this is actually just moles. So I have to calculate my concentration before I plug into my pH calculation. It's very tempting to just take this number and plug it on into pH, but you can't do that because you don't have concentration yet. It's a very, very common mistake. And even when I am working through these problems, and especially if I'm trying to go a little bit fast, I will do that and I'll have to catch myself and go, wait, you have moles, you don't have concentration. Okay, so we have, maybe we'll just put this over here. Our concentration of hydronium is going to be our moles of hydronium over our volume. And again, we haven't added any potassium hydroxide, so we're just dealing with our 15 milliliter aliquot. And that is a concentration of 0.073 molar. All right, now I can calculate my pH. So now I'm taking the negative log of 0.073 molar, and that gives me a pH of 1.13. Okay, so time for our logic check. We just have an acid in solution. It is a weak acid, but that's all we have, so we should have a pH that's low. And yes, it is low. It's 1.13, but this is the advantage of doing the strong acid first. You'll notice it's not quite as low as the strong acid, which again just kind of gives us a check. Yes, it should be acidic solution. Yes, it should be fairly low, but it's not going to be as low as, again, our nitric acid. Okay, so this was our step 1. We had no potassium hydroxide added. And now we want to go to our step 2. This is where we're going to have 5 milliliters of, again, our 0.3 potassium hydroxide added. So let's go to our next page. Step 2. Doesn't really look like a 2. There we go. 5 milliliters of potassium hydroxide has been added. And again, this is a 0.3 molar solution. I already know these moles because I've already calculated them, right? So for my nitrous acid, I have my 0.003 moles. And for my potassium hydroxide, again, I did this on purpose so it'd be easier. I have done this calculation back when I did step 2 over here. So you can see I have 0.0015 moles. That is where this number of moles comes from. But I wanted to streamline a little bit. So I am going to put in my number of moles of potassium hydroxide. And what I need to do first is I need to do a stoichiometry problem. Because I've added a strong base to this solution, that strong base is going to force the reaction forward until there's no more base left. So my first reaction is going to be my nitrous acid plus my potassium hydroxide. It is going to go forward, and I am going to form potassium nitrite and water. So again, this is my quasi-ice table. I have 0.003 moles here and 0.0015 moles for my base. I don't have anything here yet. Again, I need to determine my limiting reactant. So which one is going to run out first? Well, again, this is a great thing about having a 1-to-1 ratio because you can very easily see that my potassium hydroxide is going to run out first. So I'm going to use up all of my potassium hydroxide, and I'm going to form a little bit of potassium nitrite. So, this is should be subtract. So this one goes to 0, and of course I have a little bit of my nitric acid left, and I have 0.0015 moles of nitric acid left. And again, I formed a little bit of my potassium nitrite. Okay, so we have in solution a weak acid and its conjugate base. And I want to show this a little more thoroughly. So you might say, wait, but that's potassium nitrite. How is that the conjugate base? Well, remember, when potassium nitrite is in aqueous solution, this is a soluble salt. So it is going to form our nitrite here. And again, that is the conjugate base of our nitric acid. This means, we actually like this. This means we can use the Henderson Hasselbach equation because we have a buffer in solution. So we can use Henderson Hasselbach to calculate our pH. Now, you can also do the equilibrium calculation, and I will show that in the next step, but here we're going to use Henderson Hasselbach because I like to show several different ways, if I can, of how these things work. So Henderson Hasselbach, there are actually a couple different variations, but this is the most common one. And of course, it is my concentration of my conjugate base over my weak acid. That is a negative sign. So for my situation right here, my pH is going to equal my pKa of my nitrous acid, which I have. I'm going to have to go back to the previous page to find it. And I need my log of my concentration of nitrite and nitrous acid. Okay, so now the cool thing about this is in our last problem, we had to be really careful that we were using concentrations and we weren't just using moles. But because this is a ratio of concentrations, I can get away with actually just using moles because I'm in essence dividing by the volume in both the numerator and the denominator. Now, you can calculate concentrations and that is perfectly fine and you'll get the exact same answer. So if you want to be consistent and always calculate concentrations, please feel free. You will get the right answer. It is not a problem. I am actually going to put in moles here because I want to skip the step of calculating concentrations because I'm just, feeling a little lazy today. So pH, okay, so our pKa is our negative log of our Ka, which we'll go back here. You can see right here is 4 times 10 to the negative fourth. So this is 4 times 10 to the negative fourth plus log of, again, I'm using moles of my conjugate base over moles of my acid. And we get something really cool here. So you can see that my ratio of conjugate base over weak acid is going to equal 1. Well, the log of 1 is 0. So this whole term goes away. Makes it really easy, right? So then I just have pH equals my pKa. So I just have to do the negative log of 4 times 10 to the negative fourth, and I've got my pH. And I did that calculation, and my pH is 3.40. Okay, let's, as usual, let's do our logic check, right? Okay, so we do have a weak acid in solution, so we should have a pH that's less than 7. Now, it is a buffer, so it shouldn't be a super low pH. So having a pH of 3.4 is, kind of checking what I think it should be. Yes, it should be lower than 7, but we shouldn't have a pH of like 0.5. So this calculation looks good to me. All right, any questions about our buffer here with Henderson Hasselbach? Okay, great, yes. Fantastic. So let's go on to our next step, and I am going to need to add some more pages in here because I need some space before my titration curve. All right, so let's go on to step 3. All right, so at step 3, I have a total of 10 milliliters of potassium hydroxide that has been added. Again, it is still a 0.3 molar solution. For my nitrous acid, I still have my 0.003 moles. And for my potassium hydroxide, again, I have done this calculation because you will remember this from step 3. Again, I'll just pop back here and show you step 3 here. Again, here's our 10 milliliters potassium hydroxide. Here's where I'm getting my 0.003. We have done this calculation. It doesn't just come out of thin air. So I am at my equivalence point again. Now, when I was at my equivalence point for my strong acid and my strong base, it was just water that I had to take into account, and my pH was 7. But remember, this is a weak acid and a strong base. So when I react these two, let me just rewrite it. Plus water. I am going to make a weak base over here because, again, I'm making nitrite, which is a weak base. So let's see how much. So I'll start here again with my quasi-ice table. So I have 0.003 moles of my acid. I have the same number of moles of my base. So this is, again, kind of the trick question if you want to say which one is the limiting reactant. Well, they're both the limiting reactant. And so now I can see I have no nitrous acid, I have no potassium hydroxide, but I have some potassium nitrite. And again, it's the nitrite that's really key here. Potassium is just a spectator ion. So what we have is we have a weak base in aqueous solution. So we have nitrite, which has acid-base properties. Now it's in equilibrium, but it will make a little bit of our nitrous acid and some hydroxide. So again, the question is, how much of this am I going to make? And this is where I get to do my equilibrium problem. So I did my stoichiometry problem, and now I get to do an equilibrium problem. Okay, so from my stoichiometry, I know that I have formed 0.003 moles of my nitrite. I'm going to put both of these at 0. Again, I ignore water. I don't know how much is going to form. I don't know how far my reaction is going to go to the right at this point. Again, this is a proper ice table. It's equilibrium. So this becomes 0.003 minus x. This is x. This is x. And now I want to be really careful here. Remember, we kind of get in the habit of always writing Kas, but nitrite is a base. This is actually a Kb. And so my Kb for this is nitrous acid times concentration of hydroxide over concentration of nitrite. And that is my Kb. All right, so we need to do a little side calculation because we don't have a Kb. We only have the Ka for nitrous acid, but these are conjugate pairs. So that means that Kw is equal to Ka times Kb. So because we have the Ka for nitrous acid, we can calculate the Kb for nitrite. Okay, so that's going to be 1 times 10 to the negative 14th. And our Ka here is 4 times 10 to the negative 4th. We are calculating our Kb. So our Kb for nitrite is 2.5 times 10 to the negative 11th. Yes. All right. So, and again, it makes sense. This is a very weak base in solution, but it is still a weak base. All right. So now I have a number for my Kb. I do have my concentrations. So I am going to plug in from my ice table. All right. So this is simply going to equal x squared over 0.003 minus x, and that equals the Kb, which I just calculated. Now, in this case, you can run through your tests like we did on the previous one to check and make sure you can make this assumption that you can drop this minus x. But when you have a KB or a Ka that's 10 to the negative 11th, I guarantee you can drop that minus x. So I'm just going to go ahead and save us a little bit of time. Oops, sorry. And I'm just going to drop that. Again, feel free to go back and double check and make sure that your initial concentration of nitrite over the Kb is greater than 500. You will find that it is much, much, much greater than 500. So we can drop that negative x, or that minus x. Okay, so now we can solve for x, and x is pretty easy to solve for. So I have an x of 2.74 times 10 to the negative 7th. Okay, so this is moles of hydroxide. Remember your table here. This doesn't look like an X, but that is an X. And these are moles. I started with moles here. So what I'm going to do is just like I did at the very end of the first problem with strong acid, strong bases, I'm going to calculate POH first and then take 14 minus the POH to give me the pH. But again, you can do it a couple different ways if you like working with concentration more. All right, but first I need to take this moles of hydroxide and I need to turn it into concentration. So I'm going to make space up here. So here is hydroxide. I need concentration. I have moles 2.74 times 10 to the negative 7th moles. And I need to put this over my total volume. So remember you started with a 15 milliliter aliquot of your nitrous acid. I have added 10 milliliters of potassium hydroxide, so I have an additional 10 milliliters. So that is going to give me 25 milliliters. Now I can calculate my concentration. And so my concentration is 1.10 times 10 to the negative 5th molar. Again, make sure when you're doing this volume down here that you convert that into liters after you add it up. Okay, so that is my concentration of hydroxide. This 5 is kind of bothering me. There we go, that's better. Let's calculate POH. Is simply negative log of hydroxide, which in this case is going to be negative log of 1.10 times 10 to the negative 5th. All right, so our POH comes out to be 4.96, which means our pH is simply 14 minus 4.96, which gives us a pH of 9.04. Okay, so double check your logic. Does it make sense that we have a pH that's above 7 or we have a basic solution? Yes, it does, because we have a weak base in solution. We have this nitrite. It shouldn't put us, we shouldn't have a pH of 12. It shouldn't put us way above 7, but being above 7 does make sense. So this is the difference between your strong acid, strong base and your weak acid, strong base. So strong acid, strong base, at the equivalence point, your pH is going to be 7 because you have a neutral solution. When you have a weak acid and a strong base, your pH is determined by your conjugate base. And so usually that's going to bump you up above 7. And depending on which conjugate you're talking about, it's going to vary. But in this case, at our equivalence point, our pH is actually 9.04. Okay, questions about our equivalence point? Okay, great. No questions. Then let's keep on trucking because I know we've got one more to do and I'm going to need another page before we talk about our titration curve. So let's do another page. Okay, so we've done our equivalence point and now we're going to go one step past our equivalence point. So this is step 4. And for step 4, we have added a total of 15 milliliters of potassium hydroxide. Again, this is a concentration of 0.03 molar. Or sorry, was it 0.3 molar? It was 0.3 molar. Adding too many zeros in here. Okay, 0.3 molar. We know our moles of nitrous acid are 0.003. I think this is maybe why I keep wanting to put extra zeros in here. And then for our potassium hydroxide, again, we have done this calculation before in the previous problem, and we have 0.0045 moles of potassium hydroxide. So the first thing we need to do, just like before, is we need to do our stoichiometry problem. So first, let's do our straight up neutralization. Again, this is not an equilibrium. This is our quasi-ice table. And we have 0.003 moles of our acid and 0.0045 moles of our base. And so our limiting reactant now is our acid. So we are going to subtract 0.003 moles and then add here on the product side. So now our acid goes to 0. We just have base. And we have 0.0015 moles of base, and we've got a little bit of our potassium nitrite, our conjugate base. So what we've got now, before we jump into the rest of our calculation, is we have a strong base in solution and a little bit of a weak base. Remember what the Kb of that base was. This is a very, very weak base. So our pH at this point is going to be driven solely by our strong base. The contribution of this nitrite is so small that it's negligible. This is kind of like when we're dropping the minus x from our equilibrium calculation. This is the same thing. We do not have to worry about this concentration here for this calculation. We can solely focus on our strong base because that is what is going to determine our pH at this point. So that makes it easy because now we don't have to deal with an equilibrium problem. All we have is a strong base in solution. So remember that our concentration of potassium hydroxide, because it is a strong base, is equal to our concentration of hydroxide. And we can calculate this concentration of hydroxide because we know how many moles of potassium hydroxide we have. So for this, we're simply going to take our moles of potassium hydroxide, which is our moles of hydroxide, and we're going to divide it by our total volume. Again, this is where people get tripped up. Remember, we started with 15 milliliters, a 15 milliliter sample of our weak acid, our nitrous acid, and at this point in step 4, we have added a total of 15 milliliters of potassium hydroxide. So these volumes are additive. We have 30 milliliters total. And so again, don't forget to convert that into liters, otherwise you're going to get really screwy concentrations. We have a concentration of hydroxide of 0.5 molar. So we're going to calculate POH. See, I almost wrote pH there because you get used to writing pH, but this is a POH, is negative log of our hydroxide, which is going to be negative log of 0.05 molar, which gives us a POH of 1.3, which means our pH is 14 minus 1.3, which gives us a pH of 12.7. Okay, so logic check. We've got a pH that's very basic. Does that make sense? Yes, because we have a strong base in solution, so our pH should be very high. Again, if you get to this point and you think you've calculated pH, like I almost wrote down, because you do get used to writing down pH, it should raise some red flags because you should not have a pH that is acidic. You should have a basic pH. Okay, any questions about the calculations? All right, no questions about the calculations. I know we're starting to run out of time here, but I want to talk about the titration curve just a little bit. So here is a titration curve of a weak acid and a strong base. Again, I use this titration curve from the OpenStax textbook, so you might recognize it. It's not the same. Again, we've got different volumes of base, and I think this titration curve is actually the titration of maybe acetic acid. So it's a different weak acid. But I do want you to notice that the equivalence point here is not at 7. Now, it's not at the pH that we calculated, again, because they have a different weak acid that they're doing, but your equivalence point does not happen at a pH of 7. And you can see the shape of the curve is a little bit different because we move through this buffer region. So the pH does come up, but then it kind of evens out. Again, it's just a very different shape from your strong acid, strong base, which is very flat and then just shoots straight up when you get to the equivalence point. And then, of course, once we're past the equivalence point, we've just got a strong base in solution, and that is what drives our pH. So that is a very simple explanation of these two different titration curves. So oftentimes if you're given a titration curve, you can look at the shape and you can determine if it's strong acid, strong base, or weak acid, strong base. Okay, any questions before we finish up? Okay, great. Thank you so much for joining us tonight. Next week, there is no live stream, but I will be back the week after, and I hope to see you there. If you have requests for what you would like to see on the live stream, please feel free to shoot me an email or give me a comment and just let me know. Thanks so much. Good night.